Well, hello Internet, and welcome to part 3 of my Python for Finance video tutorial series. In this part of the video, we're going to start getting into more exciting things. I'm going to show you how to calculate risk. I'm going to show you how correlation works and how it can help you compare stocks. We're also going to look at how to manipulate data very precisely using dates, which is a question I got from a bunch of different people. And I'm also going to show you how to minimize portfolio risk by adding additional securities. And I have a lot to do, so let's get into it. All right, so to start off, just wanted to make sure everybody was aware, github.com, Python for Finance. You can download every single file I use in these videos there, for free, of course. All right, and now it's time to get into some good stuff here. All right, so at the beginning, nothing's changed. We're still using the same libraries we've used previously. And if you're a Windows user, guess what? Everything works if you just change this one line of code, which is the location of your stocks that we got in the last video. Again, there is a link in the video to download those stocks directly. And we're also going to be defining just some start dates. These are start dates for our data frame that we're working with. All the stocks that we have data on from the beginning of 2017 until August of this year, 2021, as you can see right here. And then in the last video, I showed you how to then get all of the stock names that are in your stock folder and store them in a list. And here are all of those as well. And also previously, I showed you how to go and get a data frame from a CSV file, extremely useful, and how to save a data frame to a CSV file. So all that stuff we covered previously. Now, what a lot of people had trouble with was actually using or getting proper dates from our data frame. So let's say we want all of the data from January the 1st through the end of the year of 2020. Well, January the 1st, the stock market's not open. So we want a way to just be able to say January the 1st, and it returns the first date that the stock market's open. So we're going to create a function that does that. And I'm going to call it get valid dates, and it's going to return the beginning as well as the very last date. Of course, that is valid for our specific stock that we're searching for. It's going to be passed a string for the date as well as the ending date. And if you wonder what that string looks like, it looks like this. So it's going to have the year and the month and the day. So that is the strings that are going to be passed inside of here. Now what I have to do is go and actually find them. Now, there is a potential that you search for a specific date that doesn't exist and it causes complete havoc with, this is mainly going to be the ending date for a stock in your database. So what we want to do is try to catch any potential problems we have there. Anytime we are trying to grab specific data, we are going to mask off that data. And specifically, we're looking for dates that are greater than the starting date and the ending date. So just put that in there. That is the specific part of our data we're working with, which is the dates. And there we have it. So there is our mask. Now I'm going to go and get a smaller data frame utilizing our mask. And how you do that is go df.lock and mask. And it will grab just the dates and the data between those defined dates. All right, good. Now we need to go and set our index to the date to be able to use the functions that are going to be coming up next. Otherwise, the index would just be a bunch of random numbers. We want them to be our dates. So there that is. Okay, now we need to get the smallest as well as the latest date. So the very first date in our time frame that is legitimate and the very last one. I'm just going to call this smallest date is equal to and sm, whoops, make sure like this. And then we will say index and min. And it's going to go and give us our minimum index, which just so happens to also be a date. Let's say we also want to be able to get our last date. Well, I'm going to go smaller data frame. And index and max, and that will give us our last date. All right, now problem here. We need to both add leading zeros to our date. And to do that, what I'm going to do, I'm going to call this date, and this will be the very first date. Leading is equal to. And what we want to do is, remember, I said the dates are going to be coming in this format. Well, if they come in the format of 2017-1 instead of 01, well, we need that O inside of there. So we just want to put that O inside of there. No big deal. We're going to do a join where our dashes are. So I'll say join, and then I'm going to go and say we are going to use a 0 here. Make sure you have 0 instead of O if the length of x is less than 2. So that means that there is a single number between these dashes. All right, and else, whoops, here, else, what we're going to do is just put nothing. Okay, so that's what that does. Then what we have to do is add that to our x, which is going to be the blocks of data we're going to be pulling from our data frame. And so add x, and then we need to cycle through the different numbers that are separated with this dash. So to do that, we say for x in and small date dot split, and then we need to put in what we want to split on, which are going to be our dashes. Okay, so pretty easy stuff. And let's go and copy this because we're going to do the same thing for our very last date. And I'm going to call this date ending. All right, so that's good enough. And for this guy, we're just going to change this to last date. So last date. Everything else there, exactly the same. Now what we need to do is we need to go and handle any exceptions. We shouldn't have any, but it's always good to be ready for them. So I'm just going to use the default exception, and I'm going to say that the data has been, well, let's say the date is corrupted in some way. That will draw our eyes to that specific stock, and hey, maybe something didn't download right, something, and we'll be able to go in and fix it. Then what we're going to do after this is go and return both the first legitimate date as well as the last or ending date. Okay, and there we are. So we got legitimate dates, very valuable tool to be able to utilize. Now I'm going to show you how to create a function, and what it's going to do is provide the return on investment between two dates. So that is going to be like if you invested $100 and after a year you had 120. Well, that return on investment of $100 is going to be 20. So we want that 20 number. How do we get it? Well, I'm going to call it ROI. Talked about this in the last video. So dates, we're going to get a data frame, and we're going to again get past strings for the starting date as well as our ending date. Again, we could have problems here when we're working with this data. So I'm going to throw it in a try block. And what I want to do is I'm going to say I want my starting value. So I need to get the adjusted close price for both the first as well as the last date. So df and location and s date. And specifically what we are looking for here is the adjusted close price. And we're going to do basically the same thing to get our ending value. So we'll go get this, throw that there, and then I'm going to change this to end value. And we are going to use our ending date and adjusted close. All right. Then to get our return on investment, if we just come in and go and get the ending value minus our starting value, and then we divide both of those by our starting value, and that provides our return on investment. We will go accept, and whoops, make sure you put exception inside of here, exception like this, and then we will say that our data is corrupted somewhere. Again, provides us some information to go in, make sure our files are okay, maybe download new files, and work with our data to clean it up. Okay, return ROI. Boom, done with that. Now I decided to also calculate the mean and standard deviation and coefficient of variation, all in separate functions, just to make everything much neater. So I'm going to call this get mean between dates. Again, it just provides all sorts of functionality. It's going to make it a lot easier to work with the data in our files and in our data frames. So starting date, ending date, again, strings. I'm going to go and create a mask and data frame. And we're specifically looking at dates again. And we want a date that is greater than our starting date. And we want a data frame that, again, for our date, we want a date that is less than or equal to our ending date. So there's that. We can say return and df lock, and using our mask, and we're specifically interested in adjusted closing price, and then we will say that we want the mean for that. And there we are. Good stuff. Well, when we are calculating our standard deviation, a lot of things are going to be almost exactly the same. So let's just copy this, paste that in there, and I'm going to change this from mean to standard deviation between dates. Everything else here is the same. Again, our mask usage also the same. Mask adjusted close, and just change this to standard deviation. There we are. Done with that also. And now we have to get the coefficient variation between those dates. Well, this is going to be easy. We're just going to say that I talked about coefficient of variation in the last video. Again, you should watch these videos in order. If you try to watch them in different orders, you're probably going to get confused, because while kind of simple, this knowledge that I'm providing you is sort of structured in a way to make you really understand and be able to work with all these different libraries so that you can do something useful with them. And they're just packed full of never-endingly improving functions. I start them off and they sort of work, and then I progress, and I'm trying to give you the idea of what it feels like to actually create a data science framework that we can utilize. Okay, and starting date and ending date. All right, there's our mean, and then we're going to get our standard deviation, and let's just go up here and copy this. So let's go like this. Is equal to, there's that, and then we're going to pass in the same data we passed in here. So let's do that, and then after we do this, we will return the standard deviation divided by the mean, which is the coefficient of variation. Okay, so we created all these functions. Now we need to come in here and test them. Well, I'm going to start off by getting the very first, whatever it is, ticker inside that we have here, and this is Cisco. All right, good. And let's say we would like to print out some. We don't need to do that. We could print out some information about, hey, this is this is data on CSCO, but I'm just going to skip that. All right. So what I want to do is I want to get the data frame for that ticker. I'm just going to call this stock A, and it is equal to get df from CSV, and I just pass in the tickers. Very important to test all this stuff before you start doing it live and corrupting all your data. So then we'll go stock A like this, and we can see that we were able to go in and get our indexes and our dates, our adjusted close, and our daily return. We created those in the last videos. All right, so that looks good. What do we want to do now? Well, we want to get the first and last date in a specific data range. So what I want to do, I'm going to actually print this out. And I'm going to go get and valid dates and pass in stock A, and then we'll pass in our starting date, which is going to be the very 1st of January. And then also we're going to go through the very end of the year. So there's that. And if we run it, whoops, date corrupted. Let's figure out what's going on with this. Whoops, I had a little typo up here. Just make sure this is SMDF and this is SMDF. All right. Okay, so if we do that, we can now see that we get valid dates. All right, next up, let's go and get our adjusted close mean. So adjusted close mean. And to do that, of course, we're just going to go up here and we're going to grab this. So get mean between dates. Copy that, come down here and get mean between dates and just pass in stock A instead this time. Everything else is the same. Let's go and copy this and print and adjusted close, and this will be the standard deviation. Just change this to SD between dates and the coefficient of variation. So we'll just call this COV, so COV like that, and just change this to get COV between dates, and everything else there is exactly the same. And we need to change our date to use our, change our indexes to use our dates. So we'll just say stock and A set index and the date, and you can put these in the function as well if you'd like. Just be careful not to go and make anything permanent. So, and after this, we'll go and return on investment since, and this is going to be whatever. Let's just leave this return on investment, and then we're going to pass in the different dates as well as the stock information. So this is going to be ROI between dates. So get rid of this and that. That is what it's called, right? And yes, there it is. All right, so good things there. Now if we go and make all those changes and run it, you can see, whoops, data corrupted. Let's figure out what's going on with that. Well, I know what it is immediately. Let's just change this to stock A. Boom. And you can see Cisco stock didn't do very good. So there we are. We have all of our information and everything is working. Now we know we can do this to all of our stocks. So down here, we're going to do it to all of our stocks. And we're going to create a new data frame with information on the coefficient of variation and the return on investment. So I'm going to call this get COV and ROR. It's going to be passed all of our stocks, and it's also going to be passed a starting date and a ending date like this. And what we need to do is we're going to create a new data frame with all this information. So to create that data frames, we first go and define all of the column names. So COV and let's go ROI. And then to create the data frame, we say data frame is equal to pd.data frame and pass in the columns names. So columns are going to be equal to the column names that we defined. All right, so now all we need to do is go and cycle through all of our tickers. So in tickers like this, and I'm going to print out on the screen what stocks I'm working with, because this can take some time. So I don't want you to be pulling your hair out going, is it working? So I'm going to say that I want to print out the ticker we're currently working on. Go and get our data frame now that is going to be based off of a date range. So get df from CSV first, get our CSV file and get that data. Then we're going to get our valid dates. So our eDates are going to be get and valid dates, pass in this data frame, and then the starting date and the ending date. And what else? Well, we're going to get the coefficient of variation by calling get cov between dates and pass in our data frame as well as our new starting date and our ending date. And then we need to change the index for our data frame to be equal to our index. So set index to date, like that. All right. After we do that, we can get our return on investment. So that is ROI between dates, and pass in again the data frame as well as our starting date and our ending date. And anything else? Well, of course, we need to add our stock data to a new data frame row. So to do that, we will go data frame dot location, and if we use length, it's going to give us the length of the data frame. And since it's 0 index, that length is actually going to be the next index available for us to store information into. So there's this. And what are we storing inside of it? Well, whatever the ticker is, the coefficient of variation, and the return on investment. And then after we do that for every single stock, we are going to return a data frame. All right, there we are. Now we can come in and actually calculate all this. So we're going to go get this and paste that right there. And I am going to store this in a data frame that I'm going to call market data frame equal to, there's this. And I'm going to pass in the tickers. And let's say we want to work with 2019 data, 01-01, and through the end of 2019-12-31. All right, so there is all of that data. And you can see it's printing out and it's working and it's making all of those changes and creating that data frame for us. And we don't see any problems here. We don't get, whoop, date corrupted. What's going on with this? All right, so as I was working through this, a couple bugs worked into our code here. For one thing, these stocks need to be removed. They don't have 2019 data. So just go into the folder where you have your stocks, delete all 3 of those. Another thing, this is why I do everything on Mac as well as PC. You are also going to need to go and add, only if you're on a Mac, this right here, this line of code. You want to remove that from your ticker list. That is a file that is only on Macs, so go and add that code. If you're a Mac user, if you're a Windows user, it won't do anything, so don't worry about it. And then one other slight change I made is down inside of Git, Cov, and rar, I am going to, next to sdate, mark these as 2, and edate as 2, and so forth and so on. And if you do all that, we've created our master stock data frame with all of that data that we were looking for. All right, so good stuff. And now what we're going to be able to do is if we wanted to find out which 20 stocks, let's say, had the best return on investment in 2019, we just go to that data frame and we say sort values like this and by, and specifically what we are looking for is the column ROI, and we want this to be ascending and mark that as false, otherwise it'll give you the worst performers. And let's say we want the top 20 of that group. And there we go, just that quick, we're able to find the best stocks of 2019, and a lot of them are ones you have never heard of. All right, so awesome stuff. And we can also go in there and find out the difference between the different risky stocks. All right, so got all of that set. Now what I want to do is I want to merge multiple stocks in one data frame by a specific column name. So how we can do that, I'm going to call this merge data frame and by column name. And we're going to be passed a column name and a starting date and an ending date. And then we are also going to get our ticker list. So I'm going to create a data frame here and it is going to hold data for all the data frames with the same column name. So data frame, and we created that. We want to now go for X in tickers, and we want to create a data frame here, and we'll go and get our data frame from a CSV file like that, and then df and date is going to be equal to pd dot to date time and data frame date, like we've done many times before. And then I will use a mask with our data frame here to get between the designated time frame. So greater than or equal to and the starting date, and whoops, like that, and the data frame's date here less than or equal to the ending date. And now we can say mult data frame X is going to be equal to df and lock and mask using our specific column name. All right, and there we go. And now what I want to do is I want to create what is called a correlation matrix using the FANG stocks. And correlation just tells us how closely two stocks returns move together. And correlation is a standardized value in comparison to covariance, which we'll talk about later. And the value it's going to return is a -1 to a 1. So a -1 means that these stocks returns move completely opposite of each other. So when one goes up, the other one goes down. And 1 would mean that the stocks perfectly align. That means when one stock goes up, the other stock goes up an equal amount in return. And the only time you're ever going to see something like these extremes is whenever you go and get the correlation of the same stocks. Okay, they obviously move in the same way, and this is almost impossible because no stock moves precisely the same return. And 0 just means there's no correlation. There's no comparison between the stocks. 0 is uncommon also. So you're normally going to get somewhere in between those values. And we can say that whenever this value is greater than 0.5, that these stocks are strongly correlated. So a lot of the tech stocks are going to be strongly correlated with each other. All right. And so let's come in and let's work with this. And it's actually pretty easy. So the very first thing I need to do is come in here and actually create my FANG list. So I'm just going to call this FANG list, and it's equal to, and whoops, make it a list, Facebook and Amazon and Apple and Netflix and Google. All right, so there we go. We have our list of stocks. I'm going to then go mult df, and I'm going to call merge df by column name. And what I'm specifically interested this time, we are investors, so we're interested in returns, not prices. So I'm going to say daily return, which we calculated a long time ago. And I'm going to say that I'm interested in 2020 data. And so I'm going to go from the beginning until the end. So 12-31. And then we're going to pass in our FANG list. So FANG and underscore list. All right. And now we can come in and go mult df like this. And a little typo. Let's get rid of this and put this right here. And then, of course, we need to return our data frame and run it. And then come down here and run it again. And there you can see is the entire data frame. Now, what we're interested in doing is generating a correlation matrix. So just go dot CORR like that and run that. And now you can see the correlation. Now, Facebook, of course, and Amazon and everything, they're perfectly correlated with each other. However, you can see here now, while all of these are what is considered highly correlated, you can see Netflix is not quite so correlated in comparison to the other different stocks. But you can see here that Facebook and Amazon highly correlated. Which tech stocks are most highly correlated? Google and Facebook are highly correlated. I guess Google and Facebook are the most highly correlated stocks out of this bunch. All right. So very valuable information. So that means when Google goes up, Facebook is also probably going to go up. So very useful information to look at. And what we can also do is we can go and zoom in on this discrepancy with Netflix. So what we want to do is look at the correlation between Netflix and all other stocks. So .CORR, and then just follow that up with Netflix ticker. So Netflix like this, and we can go and get that specific information. Or even better yet, what might look a little bit nicer is we can go and plot this out. And let's say we want to plot it out on a bar chart. And there we can see how Netflix and all the other different stocks are correlated. All right, so pretty cool stuff. Now, this is all about really going and zooming in and understanding risk. And variance plays into that as well. And just remember, variance is a measure of how spread out a data set is. So how much a stock's return would fluctuate. So let's say you wanted to go and get the variance for Netflix. Well, you just go mult df just like we did before, and Netflix like this, and go and call variance like that. And there you go. Now you got that variance. And what we really want to do, however, is get this in an annualized form. So we want to find out how many days we are dealing with here with our data frame. So we'll go and get our data frame and just call for index. And this will tell us how many, well, we have to go like this. Whoops, days like this. We have 253 days. So if we want to go and actually get our variance from this, what we can do is just go and get our original variance and then multiply it times 253 days. And if we do that, we're going to find our true variance annualized. Okay? So that brings us to what we call covariance. And covariance is a measure of the relationship between two blocks of data. And of course, the covariance of a stock in comparison to itself is going to be the variance for that specific stock. So what we want to do is I'm going to go and get the covariance of all of these. So to do that, I just go mult df and call the covariance function. And then we're going to multiply this times 253 again. And there you can see as well that covariance data. And that brings us to the concept of why do we care about risk? Well, most, and especially if you're an investment advisor, you'll know this is true. Most investors, no matter what they say, cannot handle massive fluctuations in stock prices. They're like, oh yeah, I'm all for risk. What that means is I'm all for high returns. Whenever they lose 20%, all of a sudden they're not going to be so risk-taking. So what we want to do at the very least is make them very aware of how dramatically their portfolio returns may be. And then what we can do at that point is show them ways that we can minimize risk by adding in other stocks that are not so closely correlated return-wise. And this is how we go and actually make calculations in regards to variance of portfolios. We have different weight values. So if you have 50% Facebook stock and 50% Newmont Mining, that's what we're going to be analyzing. A gold company that's not highly correlated with Facebook. Well, it will be 50-50. Okay, so it's how much of the portfolio is made up of the different stocks. Then we're going to have the standard deviations of the stock. Talk about standard deviation many times. And to find the overall portfolio variance, we take the weight times the standard deviation, and we add those weights and standard deviations up, and then we find the square. And since basic math, we know that this is how we're going to then be able to calculate portfolio variance, or how the returns are going to fluctuate wildly and make our client well aware of it or fix it. So what we're going to do is I'm going to create a portfolio list. It's going to be extremely simple, and it is just going to have Facebook inside of it, and it is also going to have Newmont Mining inside of it, a gold mining company. Well, I'm going to say that I want to create a data frame using this information. So I'm going to say merge df by and column name. And the thing I'm interested in is the return. So daily return. And we are going to say that we're going to go 2020-1-1 through the end of 2020-12-31. And we are going to pass inside of it our portfolio list. So I think you can see here how just creating all these different functions, making it very easy for us to do really crazy stuff. So we'll go portfolio, and let's go and get that data frame. And you can see how the returns are different. But let's come in here and generate a correlation matrix to see that they are not heavily correlated. So correlation matrix, and you can see that yes, indeed, these two stocks are not correlated, 0.19. All right. So these are two stocks that could potentially dramatically lower the risk of our overall portfolios. So what I want to do is I want to get the prices at the beginning of January 2020 to calculate the weight of both of these stocks in our portfolio. So let's go, and price df is equal to, and I'm going to call merge df by column name, like that. And in this situation, we are interested in the adjusted close. I'm doing this just so I can go and get weighting properly structured here. So from the same time period, so 2020-12-31, and then I am going to go and throw in Facebook and Newmont Mining. You can also do it this way. All right, just another interesting way to go and do this sort of stuff with your stocks. Okay, so we have that data. And what I want to do is go price and df and head. And I'm going to get these beginning prices for whenever we first started investing. So Facebook's at 209.78, let's say, and Newmont Mining's at 41.74. All right. So what I'm going to do is I'm going to say I want to buy one share of Facebook at 209.78 and 5 Newmont Mining at 41.74. This is going to make them very, very close to 50-50. Just doing that just to be able to work with fairly easy numbers. So let's say 209.78 and divided by, this is how we figure out our weightings. We take the value divided by the total value of our portfolio. So 48 like that. And the Newmont weight is going to be equal to, again, 0.70, which is 5 of those stocks. And 418, 48. Well, what we want to do is actually go and make it so that our weighting is equal to exactly 1. And that's the way weightings work whenever you're working with portfolios. So I am going to set this to 0.5012. And I'm going to set my Newmont weight to be equal to, and let's change that to 0.4988. Okay, so they equal, whenever you add them together, equal 1. Well, I'm then going to go weights and create a NumPy array, because we're going to go and dramatically simplify this formula here by using matrices and stuff that's built directly into NumPy. So let's go like this and create this, and it's going to be our Facebook weight and Newmont weight like that. And then we'll just go and calculate our portfolio variance. And to do so, you just go np dot. And what we need to do here is transpose. It's a matrix trick. And how you do that is just go and get your weights and follow that up with T, and then dot product. Again, I have tutorials on linear algebra if you're interested. I'll throw them in the description. That's where I can't really do all the linear algebra in this, plus talk about finance. All right, and we need to multiply this times 253, which is the number of days that we are tracking, and then throw in our weights finally after that. And whenever you do this, this is going to show you both our portfolio variance, as well as I will also print out the variance of the stocks on their own. And you'll see by adding them together that we were able to dramatically decrease our overall volatility of our portfolio by combining combining non-correlated stocks. And port DF, and this isn't considered an optimal investment. This is just me explaining how you bring down the risk in a portfolio. So there's that, and then we'll finally print out Newmont Mining's fluctuating value. So Newmont variance, and like that, and Newmont, whoops, NEM, like that, and run it. And you can see here our overall volatility of our portfolio, 0.12, versus the highly, well, not going to say highly, but much more risky investments. Okay, so there you go, guys. Whole lot of information, digging in deep now in investment information. Hopefully you guys found this useful, and like always, please leave your questions and comments down below. Otherwise, till next time.